This episode is brought to you by Cisco Educational Premium. We have peered into the wave equation and now we are deep in the middle of it. We already introduced the wave equation, derived it, and even studied it in different space dimensions. So we can comfortably say that we know what this guy means and how relevant it is. But just in case you need to brush up on some of the concepts, feel free to check on our earlier episodes on this. Today we will just wrap everything up, starting with the scalar wave equation in two space dimensions. In two space dimensions, the wave equation is ut is equivalent to c square uxx plus uyy. We can use the three-dimensional theory to solve this problem if we regard u as a function in three dimensions that is independent of the third dimension. If u0xy is equivalent to 0, ut0xy is equivalent to phi xy, then the three-dimensional solution formula becomes as shown, where alpha and beta are the first two coordinates on the unit sphere, and d omega is the area element on the sphere. This integral may be written as a double integral over the disk D with center xy and radius ct. As shown, it is apparent that the solution at txy depends not only on the data or on the light cone, where x minus psi square plus y minus nu square is equivalent to c square t square, but also on data that are interior to that cone. We want to find solutions to utt minus delta u is equivalent to 0 for u rn times 0 infinity going to r, with ux 0 being equivalent to gx and ut x0 be equivalent to hx. In odd dimensions, assume n is greater or equal to 3 is an odd integer, and g in cm plus 1 rn, h in cm rn for m is equivalent to n plus 1 on 2. Let gamma n be 1 times 3 times 5 and so on, n minus 2. And let u xt be as shown. Then we have utt limit of xt as the approach x00, and limit xt as the approach x00 as shown. In even dimensions, we assume n greater or equal to 2 is an even integer, and g in cm plus 1 rn, h in cm rn for m is equivalent to n plus 2 on 2. Let gamma n be equivalent to 2 times 4 times and so on to n, and let uxt be as shown. Then new utt limit as xt approaches x raised to 0 and limit as xt approaches to x raised to 0 and 0 be as shown. Let us look at reflection and transmission at the boundary of two media. For an incident wave traveling from one medium where the wave speed is c1 to another medium where the wave speed is c2, one part of the wave will transmit into the second medium while another part reflects back into the other direction and stays in the first medium. The amplitude of the transmitted wave and the reflected wave can be calculated by using the continuity condition at the boundary. Consider the component of the incident wave with an angular frequency of omega, which has the waveform as shown. At t is equivalent to 0, the incident reaches the boundary between the two media at x is equivalent to 0. Therefore, the corresponding reflected wave and the transmitted wave will have the waveforms as shown. The continuity condition at the boundary will be as shown and gives the equations a plus b is equivalent to z, a minus b is equivalent to k2 on k1, c is equivalent to c1 on c2c. And we have the reflectivity and transmittivity as shown. B on A is equivalent to c2 minus c1 on c2 plus c1. C on A is equivalent to 2c2 on c2 plus c1, where c2 is less than c1. Then the reflected wave has a reflection phase change of 180 degrees. Since B on A is less than 0, the energy conservation can be verified by B square on C1 plus C square on C2 is equivalent to A square on C1. It only holds true for any component regardless of its angular frequency omega. The limiting case of C2 is equivalent to 0 corresponds to a fixed end, and I quote, that doesn't move. Whereas the limiting case of C2 approaching infinity corresponds to and I quote, to a free end. A flexible string that is stretched between 2 points x is equivalent to 0 and x is equivalent to L satisfies the wave equation for t greater than 0 and 0 less than x, which is less than L. On the boundary points, you may satisfy a variety of boundary conditions. A general form that is appropriate for applications is as shown: minus ux t0 plus au t0 is equivalent to 0, ux tl plus bu tl is equivalent to 0, where a and b are non-negative. The case where u is required to vanish at endpoint, that is fixed end, is the limit of this condition when the respective a or b approaches infinity. The method of separation of variables consists in looking for a solution of this problem in the special form utx is equivalent to tt vx. A consequence is that t double prime on c squared t is equivalent to v double prime on v is equivalent to negative lambda. The eigenvalue lambda must be determined so that there is non-trivial solution of the boundary value problem as shown. The special case of the general problem of the Sturm-Liouville theory. If A and B are positive, the eigenvalues are all positive, and the solutions are trigonometric functions. A solution that satisfies square integrable initial conditions for u and ut can be obtained from expansion of these functions in the appropriate trigonometric series. Approximating the continuous string with a finite number of equidistant mass points, one gets the physical model as shown. If each mass point has the mass m and the tension of the string is F, separation between the mass point is delta x, and nu I is equivalent to 1 to n, are the offset of these endpoints from their equilibrium points. That is their position on a straight line between the two attachment points of the string. The vertical component of force towards point I plus 1 is as shown: ui plus 1 minus ui on delta x f. And the vertical component of the force towards point R minus 1 is ui minus 1 minus ui on delta x f. Taking the sum of these two forces and dividing with mass m, one gets for the vertical motion as shown. As the mass density is rho is equivalent to m on delta x, this can be written as shown. The wave equation is obtained by letting delta x to approach 0, in which case uit takes the form uxt, where uxt is a continuous function of two variables. Ui takes the form partial square u on partial t square, and ui plus 1 plus ui minus 1 minus 2 ui on delta x square approaches partial square u on partial x square. But the discrete formulation of the equation of state with a finite number of mass points is just a suitable one for a numerical propagation of the string motion. The boundary condition u 0t is equivalent to ult is equivalent to 0, where L is the length of the string, takes in discrete formulation the form for the outermost points u1 and un. The equations of motion are as shown, while for 1 less than I less than n is as shown, where C is equivalent to root F on rho. If the string is approximated with 100 discrete mass points, one gets the 100 coupled second order differential equations, or equivalently 200 coupled first order differential equations. Propagating this up to the terms L on C, K 0.05, K is equivalent to 0 to 5. Using an 8th order multi-step method, the 6 states can be displayed, shown. The red curve is the initial state at time 0 at which the string is left free in a predefined shape with all u.I is equivalent to 0. The blue curve is the state at time L on C 0.25, that is after a time that corresponds to the time a wave that is moving with the nominal wave velocity C is equivalent to root F on rho would need for 1/4 of the length of the string. We have the figure displaying the shape of the string at times L on Ck 0.05, K is equivalent to 6 to 11. The wave travels in direction right with speed C is equivalent to root F on rho without being actively constrained by boundary condition at the two extremes of the string. The shape of the wave is constant, that is, the curve is indeed of the form fx minus ct. There is a figure displaying the shape of the string at the terms L on Ck 0.05, K is equivalent to 12 to 17. The constraint on the right extreme starts to interfere with the motion, prevent the wave to raise the end of the string. The figure displaying the shape of the string at the terms L on Ck 0.05, K is equivalent to 18 all the way to 23, when the direction of motion is reversed. The red, green, and blue curves are the states at the terms L on Ck 0.05. K is equivalent to 18 all the way to 20, while 3 black curves correspond to the states at terms L on Ck 0.05. K is equivalent to 21 all the way to 23, with the wave starting to move back towards left. There are figures finally displaying the shape of the string at terms L on Ck 0.05, K equivalent to 24 all the way to 29, and L on Ck 0.05, K is equivalent to 30 all the way to 35. The wave now travels towards left, and the constraints at the endpoints are not active anymore. When finally they are at the extreme of the string, the direction will again be reversed in a way similar to what is displayed in the figure. The one-dimensional initial boundary value theorem may be extended to an arbitrary number of space dimensions. Consider a domain D in a m-dimensional X space with boundary B. Then the wave equation is to be satisfied if X is in D and t greater than 0. On the boundary of D, the solution U shall satisfy partial U on partial n plus AU is equivalent to 0, where n is the unit outward normal to B and A is a negative function defined on B. The case where U vanishes on B is a limiting case for A approaching infinity. The initial conditions are U 0x is equivalent to fx, ut 0x is equivalent to gx, where f and g are defined in D. This problem may be solved by expanding f and g in eigenfunctions of the Laplacian in D, which satisfy the boundary conditions. Thus, the eigenfunction nu satisfies del v plus lambda v is equivalent to 0 in D, and partial v on partial n plus AV is equivalent to 0 on B. In the case of two space dimensions, the eigenfunctions may be interpreted as the modes of vibration of a drumhead stretched over the boundary B. If B is a circle, then these eigenfunctions have an angular component that is trigonometric function of the polar angle theta multiplied by a Bessel function of integer order of the radial component. If the boundary is a sphere in three space dimensions, the angular components of the eigenfunction are spherical harmonics, and the radial components are Bessel functions of half integer order. The inhomogeneous wave equation in one dimension is as the following: utt xt minus c square uxx xt is equivalent to sxt, with initial conditions given by ux0 is equivalent to fx, ut x0 is equivalent to gx. The function s xt is often called the source function because in practice it describes the effects of the sources of waves on medium carrying them. Physical examples of source function include the force driving a wave on a string, or the charge or current density in the Lorentz gauge of electromagnetism. One method to solve the initial value problem is to take advantage of a special property of the wave equation in an odd number of space dimensions, namely its solutions respect causality. That is, for any point xi, ti, the value of uxi, ti depends only on the values of fxi plus cti and fxi minus cti, and the values of the function gx between xi minus cti and xi plus cti. This can be seen in D'Alembert's formula that has been shown, where these quantities are the only ones that show up in it. Physically, if the maximum propagation speed is c, then no part of the wave that can't propagate to a given point by a given time can affect the amplitude at the same point and time. In terms of finding a solution, this causality property means that for any given point on line being considered, the only area that needs to be considered is the area encompassing all the points that could causally affect the point being considered. Denote the area that causally affects point xiti as Rc. Suppose we integrate in homogeneous wave equation over this region as shown. To simplify this greatly, we use Green's theorem to simplify the left side to get as shown. The left side is now the sum of three line integrals along the bounds of the causality region. These turn out to be fairly easy to compute. In the above, the term to be integrated with respect to time disappears because the time interval involved is 0. Thus, dt is equivalent to 0. For the other two sides of the region, it is worth noting that x plus or minus ct is a constant, namely xi plus or minus cti, where the sign is chosen appropriately. Using this, we can get the relation dx plus or minus c dt is equivalent to 0. Again, using the right sign, we get as shown. And similarly, for the final boundary segment, we get as shown. Adding the three results together and putting them back in the original integral, we obtain the equation. Solving for uxiti, we arrive at uxiti as shown. In the last equation of the sequence, the bounds of the integral over the source function has been made explicit. Looking at this solution, which is valid for all choices xiti compatible with the wave equation, it is clear that the first two terms are simply D'Alembert's formula, as stated as a solution of the homogeneous wave equation in one dimension. The difference is in the third term, the integral over the source. For one-way propagation, that is, waves are traveling in a predefined direction, plus C or negative C in homogeneous media. Wave propagation can be calculated with a tensorial one-way wave equation, resulting from factorization of the vectorial two-way wave equation, and an analytical solution can be derived. In 3 dimensions, the wave equation, when written in elliptic cylindrical coordinates, may be solved by separation of variables, leading to the Mathieu differential equation. The elastic wave equation, aka Navier-Stokes equation, in 3 dimensions describes the propagation of waves in isotropic homogeneous elastic medium. Most solid materials are elastic, so this equation describes such phenomena as seismic waves in Earth and ultrasonic waves used to detect flaws in materials. While linear, this equation has a more complex form than the equations given above, as it must account for both longitudinal and transverse motion. By using del cross u is equivalent to del dot u minus del dot u is equivalent to del dot u minus del u. The elastic wave equation can be rewritten into more common form of Navier-Stokes equation. Note that in the elastic wave equation, both force and displacement are vector quantities. Thus, this equation is sometimes called the vector wave equation. You can see that if f and del dot u are set to 0, this becomes Maxwell's equation for the propagation of the electric field E, which has only transverse waves. In dispersive wave phenomena, the speed of propagation varies with wavelength of the wave, which is reflected by a dispersion relation. Omega is equivalent to omega k, where omega is the angular frequency and k is the wave vector describing plane wave solutions. For light waves, the dispersion relation is omega is equivalent to plus or minus c absolute value of k. But in general, the constant speed c gets replaced by a variable phase velocity v. P is equivalent to omega k on k. Cisco Educational Premium is a section of Cisco Educationals with content that is not hosted here. There are episodes ranging from long to short videos. Remember those good old shots of ours? They are there. So do we get there? Use the link on screen or in the description or in the pinned comment below. Enjoy yourself. And I will see you in the next episode of Cisco Educationals.